All right. So we're going to sort of break up the world of biochemistry into different classes of molecules. And the first one we're going to be talking about are carbohydrates. All right, these are sugars and starches. They're given this name carbohydrate because they all have this formula where however many carbons they have twice as many hydrogens and that same number of oxygens, right? So for every carbon, there's a water in our sugar. But that is very deceiving in terms of the structure of a sugar. It's not a bunch of water molecules that are bound to those carbons. That doesn't really make any sense. So the structure of a sugar is just a carbon chain that has a whole bunch of alcohol groups on there. Right, so each carbon has an OH group. And then one on the end, actually it doesn't have to be in the end, it can be on the second carbon as well, but whatever, is a carbonyl group. All right, so we got a bunch of carbons and oxygens. And what the body uses sugars for, or carbohydrates for, is you take this sugar and you mix it with O2, and you get CO2 and some other products, but in a whole bunch of energy. CO2, probably water. All right, this isn't exactly a balanced chemical equation here. All right, but that's what we use our sugars for, is we use them to convert into energy. The body likes to use it to create these molecules called ATP, which it packages and then uses for energy later on. But yes, this is really not much different than a combustion reaction, the reactions that power like our cars and stuff like that. It's again using this fact that when you're creating a bunch of new carbon and oxygen bonds, like in CO2, that releases a ton of energy, right? It's not quite a carbohydrate. There's a bunch of, it's not quite a hydrocarbon. There's a bunch of OH groups on there as well. But why wouldn't the body be able to use a hydrocarbon as a source of fuel? Right? Like, what's the difference between these molecules here? Yeah, one's soluble in water, right? Like, our body's not going to be able to have a bunch of pentane floating around, right? So instead, we use these sugars, and they're really just these long carbon chains with a bunch of OH groups to make them soluble. But then our body does the exact same thing that our car engine's doing. It's going to oxidize each one of these carbons and use that as a source of energy. All right? So this is our sugar here. This is just a random example of a sugar. This is not how biochemists like to look at sugars. All right? So biochemists will take these structures. These are our normal organic chemistry structures. And they sort of look at it, the same molecule, this exact same molecule, but we're going to like rotate about these carbon bonds so that now all of these groups are sticking up at us here. All right? This is kind of the way that they like to look at sugars here. And you can see that we have different orientations of these OH groups. Some hydroxyl groups are on the left. Some hydroxyl groups are on the left, right? So there's different orientations. Notice how each one of these carbons would be considered a chiral center, right? Each one of those carbons has 4 distinct bonds. So there's a lot of different sugars out there, glucose and galactose and blah, blah, blah. And the difference between them is the orientation of those OH groups. Is it an R or an S carbon? All right, so this is the way that they like looking at sugars. Let me get this, ignore this real quick. Okay, so they take this molecule and they create what's called a Fischer projection. So again, we kinked that molecule so that those those hydrogens and hydroxyl groups are all pointed out at us. And then they just represent it with a train track here. And this is what's called a Fischer projection. you can make a Fisher projection of any molecule in organic chemistry. We just really don't, unless like this is, like you could, and maybe somebody would find a use for it somewhere, but it's a very, very rare form of looking at molecules in organic chemistry. But for sugars, they love looking at these types of Fisher projections here, all right? And there's two main reasons for that. We can see the orientation of the OHs and the H's, right? We can see very easily the chirality of each one of those carbons. Is the OH group on the left or on the right? All right? But if we took this thing and we sort of are looking at it as if it's stretched out here, remember carbon bonds aren't linear. So if you took a molecule and you kinked it like that, you'd actually kind of be wrapping it around to create this ring. And that's the other reason why they like representing sugars using this Fisher projection, is because sugars do indeed make these rings here, all right? One reaction that's really important in sugar chemistry, which is a reaction that we covered, is that if you have a ketone and you mix it with an alcohol, let's just do ethanol, you will first get what's called a hemiacetal. So that alcohol acts as a nucleophile. And what's going to be the electrophile? That electrophilic carbonyl carbon, yep. All right, so we get this new bond where this oxygen from our alcohol is now attached to that carbonyl carbon. And we said that it wouldn't stop here. It would react with another molecule of the alcohol to create a acetal. And so this reaction, because these sugars have both carbonyl groups and alcohol groups in them, they undergo these intermolecular acetal reactions. Right? So what ends up happening is one of the OH groups, it's actually this one down here, is going to act as our nucleophile. I think I always do nucleophiles in blue. So and it's going to attack that carbonyl carbon. And this will form this six-membered ring where oxygen is a member of that ring. Right here. All right, and sugars, they're constantly kind of in equilibrium between the closed ring and the open form, back and forth, back and forth, back and forth. But importantly, the way that your body uses it is in that closed ring. And so again, people who study sugars like to look at these ring structures. And I'll show you why looking at the Fisher projection makes it really easy to see how those OHs are going to be oriented on the ring as well. All right? So first of all, this carbon that was my electrophile is this carbon right here. And that OH group that forms on that carbon is of unknown stereochemistry. It could have pointed up, it could have pointed down. You're going to get a 50-50 mix of both of them. Okay? This is what's called the anomeric carbon of the sugar. But all my other OH groups, I can tell based on my Fisher projection whether they're going to be pointed down or up, right? Their orientation is fixed about this ring. What we're going to see is that all the OH groups that are on the left-hand side, they're going to be pointed up when my ring closes. And all the OH groups that are on this side are going to be pointed down when my ring closes. So, okay, so we got this carbon. We said we don't know what the OH group is there. But if we move on to the next one, that means that this carbon over here is going to have its OH group pointed down. If I look at my next carbon, let's just number these actually. Carbons 1, 2, 3, 1, 2, 3. All right, carbon 2, the OH group is on the left, so that's going to be pointed up. And carbon 3, the OH group is pointed down. All right. The next one, on carbon 4, where'd that OH group go? One, two, three, four. That was my nucleophile, right? That was my nucleophilic oxygen over here. So then I have to go for carbon 5 is going to be up here with its OH group sticking off. All right, but we can tell the orientation of those hydroxyl groups about this ring based on that Fisher projection. All right, so why would they look at this really weird representation of this molecule where everything's all kinked around? Because they're sort of anticipating this ring closing and they want to demonstrate how those hydroxyl groups are oriented about that ring. All right, so if we look at all the different sugars here, we got a bunch of different sugars. Let's just look at, this page is going to look really scary. It's not like we have to know these names or know these structures. There's nothing about memorizing here. This is just simply a nice figure depicting all of these different sugars that exist. All right? And so if we look, we start out with our 4 carbon sugars up at the top here. And how do these differ? They differ by the orientation of that OH group. Whoa. It turns out that the bottom OH group, that last one that acts as the nucleophile, the body has like this specificity where it only picks one of those 2 possible orientations. And that's what the D stands for outside of this sugar. If this was an H over here and an OH over here, it would be called an L sugar. Again, not really something you have to know, just fun fact. The body only processes like D sugars. Right? So we have this kind of specificity for that one particular carbon in these sugars. All right, and then we can go on. We see that if we get 1 carbon extra, now we have a bunch of other possibilities. One where our OH groups are both on the right, one where one on the left, the other's on the right. They're both on the left, right? So the only difference between all these sugars are the number of carbons and then the chirality of each of those carbons in your backbone, right? Which side is the OH group pointed on? Okay, and so that first reaction would be forming this sort of hemiacetal here. I guess we did this one. All right, and that's what we call this thing. Again, this is that ring closing reaction of sugars. Sugars will also undergo another reaction to form that full acetyl, and that's when sugars get packaged together to form starches. All right, so then they'll have this acetyl bond connecting those 2 rings together, and that's how your body sort of stores those sugars. If you accidentally take in too much sugars in your diet, a caloric excess, your body will create these starches and then kind of package them into the corner of the cell or something like that to be used later on. Cool. All right, so that is our discussion of the biomolecule of sugar, but it brought up a few things that we haven't talked about in a while, and so let's review those things. All right, so the first one being chirality. So, strictly speaking, the definition of a chiral molecule is that its mirror image is not superimposable. I'm not sure how to spell imposable. That's pretty close. Anyways, so yes, that would be a chiral molecule. And so the classic example of like, well, what the heck does that mean? So the classic example is your hands, right? Your hands are example of chiral things. I guess they're not molecules, but right, they're very close to one another. They look very similar, but if you take them, you can't quite superimpose them on top of each other, all right? They are in fact mirror images of one another. So we have the same thing with chiral molecules. So let's just look at an example. All right. So this molecule right here is a chiral molecule. And there's kind of a dead giveaway that we can use to spot these chiral molecules. We call those chiral carbons. How do you spot a chiral carbon? What's the rule? What's up? 4 distinct groups. Yeah, 4 distinct groups are bound to that carbon. All right. And the thing is if we took this molecule here, what makes this got this special sort of chirality business is if instead we put that bromine on a dashed bond, these are 2 distinct molecules. These are not the same. These are what would be called a pair of enantiomers, or mirror images. All right, and so that's part of why we're going to review this, is there are some funky sounding words in this discussion of chirality that we just want to remember. They're not too bad. All right, but again, an enantiomer is a mirror image pair of molecules. Stuff's about to die. Okay, and so if we name these 2 here, they would both be 2 bromobutanes, but that's not enough to specify them because, as we said, these are 2 distinct molecules here. All right, so again, these are 2 bromobutanes. This one's also a 2-bromobutane, so what do we got to include in the name to sort of finish off the name of this molecule? Yeah, the RS, right? So we got this assigning R and S chirality. It's been kind of a minute here, so let's go over. I guess RS stereochemistry. All right, cool. So let's just use that first 2-bromobutane as an example here. All right, so we said that there are 4 distinct bonds about that chiral carbon. What's missing here? I only see 3. That implied hydrogen, and what type of bond am I going to put that hydrogen on? It's got to be on a dashed bond. All right, so assigning R or S chirality here. Step 1, we have to assign priority, numbering 1 through 4, of each of those groups about that chiral carbon. All right, so step 1, assign priority. What is priority based on? Was it? Not electronegativity. Like, for example, iodine would be way higher priority than carbon. Yeah, not size, strictly speaking, number of protons, atomic number. Just simply the tile on the periodic table. That is how you decide priority. Atomic number. So then which one of our groups here is the highest priority group? That bromine, definitely. So then which one of these is the lowest priority group? Hydrogen, because it's atomic number 1. It's definitely going to lose. All right. Now if I look at these other two groups, these are both carbons that are attached to that chiral carbon. So that's tied, right? If I look at carbon and a carbon, they're both element 12. So how do we break our tie? We're going to list everything that those carbons are bound to. So I'm going to make a list above each carbon. This one is bound to 1 carbon and 2 hydrogens. And what about my methyl group? What is that bound to? Just 3 hydrogens. And this, now again, I'm just going to compare atomic numbers. And so because I'm comparing this carbon and this hydrogen, that methyl group loses. Right? So when you get a tie, you list everything that those are bound to. So cool. So again, that makes U2 and U3. All right. Let me sort of move away from all of these markings so we can make this a little bit more clear. All right, then remember now we're going to connect 1 to 2, 2 to 3, and 3 back to 1. That's step 2 here. One to 2 to 3, back to 1. All right, and what we're looking for is, did we make this little loop in the clockwise direction or the counterclockwise direction? So after we connect, does anybody remember which one's which? R is clockwise, S is counterclockwise. All right, but we got to put one sort of important caveat in front of this. And that is, if that last priority group, the lowest priority group, is pointed into the page, if it's pointed into the page, then R is clockwise and S is counterclockwise. Does anybody have a good way of remembering that? Okay, all right, I like that. See, I'm like counterclockwise has an R and it's S, and I feel like that's a terrible way of remembering it. I'm always having to like coach myself through it and make sure I've got it correctly. But anyways, I like the regular clock method. All right, cool. Okay, cool. So then what if we have our other, so then we establish that this one is going in the clockwise direction, so that would be our R. All right, so then obviously the mirror image, it's an enantiomer, is the S. But let's take this as an example here so we can make a point. All right, if I don't change my bonds, I'm going to assign my priorities the same, right? The only difference is that in this molecule, there's a hydrogen sticking out at us on a wedge. My priorities are the same. All right, so what we could do is redraw this molecule. Like, imagine that we pick it up with a spatula and flip it over like a pancake, and we could redraw it like that so that that hydrogen is pointed into the board. But that's a rather tricky thing to do, and it seems like we're kind of error prone in that sort of approach, right? It's easy to make a mistake and kind of mess it up. So the easier thing to do here is, instead of flipping over the structure, to flip your rules. So instead, if that lowest priority group is pointed out of the page, then instead of flipping over our structure, we're going to flip our rules. And so now it would be R that would be counterclockwise, and S that would be clockwise. All right, and so you could imagine, you could redraw your molecule and sort of do it that way, but again, that's kind of an easy way to make a mistake. It's easier to just be like, oh, I need to flip this, let me flip my rules around, all right? And so that way we can see that, again, we go in this clockwise direction, but because that lowest priority group is pointed out of the page, we have the S configuration. All right. So, I don't know, we've looked at some bonds with this, with these dashes and wedges. What we really haven't talked about, even a little bit since the first semester, that's closely tied to this, is what's called optical activity. All right, going back to our bromobutanes here. Is our bromobutane going to have a different boiling point than S-bromobutane? No. Is it going to have different reactions than S-bromobutane? Like, is it not going to undergo a elimination reaction or something like that? No, they have the same reactions. They have the same physical properties. They have the same boiling points, molecular weight, all that jazz, all right? The big difference between these two, the only real way that you can measure the difference between these two enantiomers would be what's called optical activity, all right? So it turns out that a chiral molecule will rotate light. Sort of scatters light in a way that rotates it. We went over this kind of in detail. I don't want to dive too much into this. The bottom line is, if you took a sample of our bromobutane and you put it in this fancy little spectrophotometer that measures optical activity, you would see that the light that you sent in was bent a little bit after it went through your sample. All right? And that's the only thing that's going to be different about these two. So let's say that we took our 2-bromobutane, our R2-bromobutane, and we put this into this instrument here. What we would get out as our measurement is this alpha in a box. All right, this is your optical activity. This is the symbol that they use. And you would get a number, like 18.3 degrees. Which meant you sent a sample of light in that was at 0 degrees, and it rotated it 18 degrees, 18.3 degrees as it went in there. Right? You shot in a beam of light at one sort of angle, and it rotated it. All right? And so the magical thing here is, if then we took that sample of the S2-bromobutane, and we stuck this in that exact same instrument, it would also rotate plane polarized light, and it would also rotate it 18.3 degrees. It would just be in the opposite direction. So this would rotate plane polarized light negative 18.3 degrees. No, there's no, the number, the sign, there's no way to look at a molecule and know what that will be. Yep. All right. So then there's this sort of terminology that also accompanies this phenomena. People will call a molecule optically active. And that is the exact same thing as calling a molecule chiral. Those are 100% synonymous with one another. Okay? A molecule that is chiral will rotate plane polarized light, so is optically active. So anyways, those are one and the same. They are synonyms of one another. If something is optically active, that means that it is chiral, and vice versa. All right? There's sort of an important exception to this sort of discussion of, how we spot chiral molecules, and those are what are called meso compounds. All right, meso compounds have chiral centers. But they are not chiral. They are not different from their mirror image. If you took their mirror image, you could indeed superimpose it on that structure. Even though they have these chiral centers, they are not chiral. So these would be called achiral, not chiral. The fancy way of saying not chiral is saying achiral. And again, that means that it's not optically active. So these meso compounds, they have chiral centers, but they're not optically active. They are not themselves chiral. All right, so let me show you an example, but let me make a point real quick. When I drew these two enantiomers, I used this little trick of just taking my dashes and converting them to wedges, or vice versa, right? That's how we can draw the mirror image of a molecule pretty easily. We can do, it's a little bit more work, but we can also take that molecule and draw its mirror image by saying, all right, I'm going to put a mirror here. Let me draw its reflection. Right, so now this one's up over here, so I'm going to start over here and then go down. So now this carbon has to be the one with my bromine on there. So then the next one goes up. Boom. Right, so I could have drawn my mirror image by doing it that way, by imagining there was a mirror and drawing that reflection. So that means, importantly, these are the exact same molecule. And that is something that is very difficult to see and is still kind of tricky for me. I could kind of imagine that I'm going to pick up this molecule and flip it over, and then I get the bromine pointed in the other direction, but it is sort of like a little bit of mental gymnastics to see that those are the exact same molecule. If you had a model kit, you could see it very easily, right? You could take that thing and spin it around, and then you would see that those are one and the same structure, all right? Okay, so then to make a point about this meso compound here, let me take a really classic example of a meso compound. To be honest, the most common one that you run into would be a cis cyclohexane compound. All right, so let me imagine I'm going to take my cyclohexane ring, and I'm going to add two identical groups on the same side, so the cis isomer here. And it doesn't matter what you put on there as long as they're identical. I'm just going to stick with my bromine example. This is a meso compound. All right. Do we have chiral centers? Yes. Each of these carbons right here are chiral centers. So again, a meso compound contains a chiral center. But now, if we were to take this thing and draw its mirror image, right? You can just see that its mirror image is identical. So even though this molecule here contains chiral centers, It is not itself chiral. It is an achiral molecule. And again, these have these special fancy names, these meso compounds. Does anybody remember how we spy a meso compound? Like you could draw the mirror image, but sometimes it's not as obvious to see it that way. It's got a plane of symmetry, exactly. You can fold it, right? Exactly. So if we just look at our cis 1,2-dibromobutane here, we can note that right down the middle, it has this plane of symmetry. Within the molecule itself, there's a plane of symmetry in a meso compound. All right, so then last little bit of vocab here with regard to these chiral compounds. Let's now look at an example of a molecule that is not a meso compound that has two chiral centers. I'm going to put a hydroxyl group on one and a bromine on the other. All right, and I want you all to take a second and draw me the enantiomer of this molecule. All right, so if I'm going to do I'll do it the easy way here. I'm just going to flip both of these wedges to dashes, and that creates my mirror image. All right, so then what if I just took one of these? I'm going to just take that hydroxyl bond, and I'm going to flip that one, but I'm going to leave the bromine the same. All right, importantly, these are all considered stereoisomers of one another. Stereoisomers, they have the same connectivity of all these atoms, just oriented differently in space. So all these would be considered stereoisomers. But only this pair right here would be enantiomers of one another, because these two are not mirror images of one another. All right, I flipped one of the groups, but not both of them, so these are not mirror images. So we also have a fancy name for these pairs here. These are what are called diastereomers. All right, so then what about these two here? If I selected these two, what's their relationship? Are they enantiomers or diastereomers? They are also diastereomers. Right, so to be a pair of enantiomers is a pretty strict kind of set of rules there. But this molecule does have an enantiomer, so let's finish out our box here. We have one more stereoisomer we can draw of this compound, of this 2-bromo-3-butanol here. So again, I have another pair of enantiomers. To finish this off here, these two would also be diastereomers. I'm just going to use a D for that because I'm going to get lazy. And these across from one another over here are also diastereomers, right? So again, to be an enantiomer pair, it's kind of a strict criteria. You have to be mirror images of one another. All of these, though, would be considered stereoisomers of one another. All right, so again, just kind of throw in some vocab that we haven't heard in a long time here with the diastereomers and the enantiomers. And so then the last one here that I want to throw at you is what's called a racemic mixture. All right, a racemic mixture is a 50-50 mix of all or of a pair of enantiomers. Right, so 50% R, 50% S. Some reactions that we discussed, so for example, SN2 reactions are stereospecific. They'd only produced one of the two possible isomers. Other reactions, ones that go through carbocation intermediates, always produce racemic mixtures, 50-50 of both. So if we had a racemic mixture, would we expect it to be optically active or no? So it's 50-50 mix of the R and the S. And remember, the R's are all going to rotate in one direction, and the S's are all going to rotate the exact same amount, but in the opposite direction. So a mixture of pure R or pure S would be optically active. But if I have a racemic mixture, a 50-50 mix of both, it's not going to be optically active. That light's going to come out the exact same way that it was went in there. So yes, so let's just make a note. Racemic mixtures are not optically active. Cool. All right, so just a quick crash course in first semester, whatchamajiggy, stereochemistry. One more that I think is everybody's probably a little bit better at, but just to be sort of thorough and go through real quick, we can also have alkene stereochemistry. And then we don't use R or S, we use what? E and Z. So E and Z, assigning E and Z stereochemistry. All right, and we did practice this a bit this semester, so let's just go through it kind of quick here. All right, step one, we're going to chop at our double bond. All right, we're going to assign high and low priority on one side of that double bond. So we're going to pick the left side first, and then do the same thing on the other side. All right, the biggest mistake that people make when they're doing their E and Z stereochemistry is to accidentally mix it up with a chiral with an R and S, and they label 1 through 4. You're not labeling 1 through 4. We're going to look at one side of this double bond and assign high-low. All right, so let's look on the left-hand side of this bond here. I have an ethyl group and a methyl group. Again, both are carbons. They're tied, so I got to list what they're bound to. An ethyl group is bound to 1 carbon and 2 hydrogens, where a methyl group is bound to 3 hydrogens. So which one's my high priority group? The ethyl group. My methyl group is my low priority group. And now I'm going to jump to the other side, and I'm going to do the same thing, assign high or low, right? So I'm not comparing groups on opposite sides. I'm only comparing the 2 groups on the same side. If we look over here, what 2 groups am I comparing? A methyl group and what? That implied hydrogen. And of course, hydrogen being the smallest element on our periodic table, the lowest atomic number, will always be your low priority group. So that methyl group is high. All right, so in this case, my high priority groups are on opposite sides. So that makes this which one, E or Z? E, and remember we had that stupid way of remembering it, that Z meant that those 2 high priority groups were on Z, same side of the molecule. And that's just some stupid little phrase that'll help you never forget how to assign E or Z priority. E means they're on the opposite side. We don't have a fun one for that. What? E cross, there we go. Nice, they are E cross from one another. I like that. All right, so then this molecule here, to finish this off, 1, 2, 3, 4, 5. So this would be now E, what is that, 3-methyl, 2-pentene. Cool, so for chiral compounds, we have RS assignment. For alkenes, we have this EZ stereochemistry. Okay, and then lastly, for this molecule here, what would this one be, E or Z? Or trick question? Trick question, all right? And how can we spy it's a trick question? Identical groups, right? If I tried to do it here, I would chop at this line, and I'd be comparing a methyl group with an identical methyl group. One of those can't be higher or lower, right? So this has no E or Z stereochemistry. And we can spy that because we have these 2 identical groups on that same carbon. All right. So then the last thing that we're going to use this discussion of sugars to talk about is we talked about how they form these 6-membered rings, and I think it's been quite a while since we've talked about these chair conformations of cyclohexane. Right? And so what we want to do is why did we use these things? So we said, all right, here's a cyclohexane, and we're used to looking at these in our bond line structures. That's how we look at all of our molecules. All right, so then let's put some methyl groups on here. But just by looking at this molecule here, we're not getting, by looking at this bond line structure, we're not getting all of the information about this molecule, because it turns out that cyclohexane adopts a very specific conformation we call a chair conformation. And so we want to take this structure here and sort of turn it into this chair conformation. And that'll just help us better understand the orientation of these methyl groups. All right, so how do we draw a chair structure? We're going to draw first two parallel lines with the bottom one extended out a little bit further than the top one. So this was my step one, is to draw these two lines. All right, when we go to step two, we're going to connect those with a triangle. So this was my step two after I drew those two parallel lines. This is what I got. All right, and we can check our chair structure. Because if we look at these 6 carbons, they should have a specific kind of orientation. What I mean by that is that 3 of them should be sitting at these peaks here, at the tips of a triangle. Every other carbon is at a point. And then every other one, the ones that we're missing here, these are all at the bottom of a triangle. They're at a valley here. So we got points and valleys every other. Right? Point, valley, point, valley, point, valley, going around that ring. And that's how we can check that we have our structure drawn correctly. All right, and every one of these carbons has 2 types of bonds, axial and equatorial. The points have their axial bonds pointed straight up. So every other has an axial bond that's pointed straight up out of that ring. And the valleys also have axial bonds, but they're all pointed straight down. All right, so these are axial bonds in both of these carbons, but they're pointed in different directions in our chair structure. And then the 4th bond on each of these carbons we call which position? The equatorial. So they also all have one that's pointed straight out of that ring, what's called the equatorial position. All right, so again, we're trying to use this chair structure here to better understand this thing here. All right. So all of these carbons are pointed up, like out of the page according to that bond line structure, right? Because they're all on wedges. So if I'm looking at my chair conformation, it's as if I'm looking at this molecule from up above, right? So here's my eyeball, and I'm looking down at this molecule. That's what I see when I look at my bond line structure here. All right, so let's call these carbons 1, 2, and 3. And we're going to do the same thing in our chair structure, try to match them, carbons 1, 2, and 3. Okay? So on carbon 1, if I'm looking at the top of this molecule, I'm looking down here. Here's carbon 1 in my bond line structure. It's got a methyl group pointed out. Here's carbon 1 in my chair structure. Which one of those bonds should that methyl group be on? The axial position or the equatorial position? If I'm looking from the top and it's pointed up at me, it would be that axial position. So this we're going to call, this methyl group right here is in the axial position. All right, so now let's move down the line here. Let's go to carbon 2. Again, that methyl group is pointed out at me. If I'm looking down at this structure, would that be the axial position or the equatorial position? It would actually be the equatorial position because the axial position is pointed straight down, right? So if I'm looking here, now I'm at the equatorial position. And then if I move to carbon 3, what's my position? That would be the axial. Oh my gosh, sorry, this thing keeps on dropping. That would also be the axial position. So notice how it's every other axial, equatorial here. They're pointed out on the same direction according to my bond line structure, but because of this chair conformation, I know that it's actually in the axial position, and then the next one is in the equatorial position. All right? And then lastly, I chose one of the two possible chair structures arbitrarily. Remember, these chair structures can undergo what's called a chair flip. And this will not change your bond line structure at all. But in a chair flip, all of your axial bonds are moved to the equatorial position, and all your equatorial bonds are moved to the axial position. So now it goes equatorial, axial, equatorial. This is what we call a chair flip. Again, the equatorials become axials, the axials become equatorials. Didn't change my bond line structure, right? It would have, we could draw a different chair, but I'm sort of trying to get at the fact that that's not really necessary, as long as we can kind of see what's going on by looking at these bond line structures. All right, so let's do a similar example. I lied. We have one more thing to do here. The other thing that we can do is we can look and ask, what is the more stable conformation? Does anybody remember what logic we used to figure out what the more stable conformation would be? These big groups, and the bigger it is, the more it's true. They prefer one of those two positions, axial or equatorial, the equatorial position. There is just more room. We sort of looked at these structures. There's just more room when that methyl group is sticking out. If it's pointed straight up, it's kind of all crowded, right? So which one is the more stable conformation? What we said was that large groups prefer the equatorial position. So then which one, left or the right? Which one's going to be more stable? Right, yes. So this one we can say would be more stable. All right, cool. So I want to do two examples of these kind of problems to sort of hammer home these patterns about what we can see. Because yes, you can take the time and draw your chair conformation and all that jazz, but you kind of don't need to, as long as you can kind of understand what's going on. And I think these two examples will hopefully illustrate that. So we're going to take a ring, and now on each of these 6 carbons, we're going to put a methyl group on there, and they're all going to be pointed in the same direction. So we got 1, 2, 3, 4, 5, 6 hexamethyl cyclohexane here. All right, with all of these methyl groups on these wedges. Okay, and if we drew a chair structure, you can sort of arbitrarily pick your chair structure that you start out with. So what I'm going to do is I'm going to say first, this one, this top methyl group here is in the axial position. And I want you to tell me what all of these other methyl groups are going to be in. And then I want you to tell me the same thing after the chair flip has occurred. Okay, and then we're going to do a similar example, but now I'm going to make every other one pointed in the opposite direction. Again, this one's going to be in the axial position. And you're going to give me what happens after the chair flip. All right, so first of all, if this first one is axial, what's the next one going to be in? What position? Equatorial. And then the next one would be axial, then equatorial, then axial. So again, that kind of every other pattern that we can spot here. When we do our chair flip, importantly, I'm not going to change my bond line structure at all. I'm just going to change my interpretation of the orientation here. My axial bonds will have become equatorial, and the equatorial bonds will have become axial. So again, we see that every other pattern in the opposite direction. So then, which one of these would be more stable? They're the same. All right, if we do the next one, that example here, all right, we said that if this bond was a wedge, it would be in the equatorial position, but now it's on a dash, so it's in the axial position. And then this one's in the axial. So then all of these are in the axial position. My chair flip. All my axials are going to become equatorials. So then are these equally stable? No. Which one is preferred? The one on the right. Yeah, this one's way more stable. All right, so my point sort of being is that if we can spy these patterns, we can kind of get a little bit better at looking at just any structure and being able to see in our mind's eye what the axial and equatorial distribution is going to be. So let me just give you an example of the type of problem using these patterns without even having to actually draw your chair structure. Like if I gave you this. And I said, what position is the methyl group in the most stable conformation of that molecule? All right, let's just play this same game. We're going to say, doesn't matter, this one's in the axial position. Tell me what this group over here would be in. And then do the chair flip, and let's take a look. All right, so if we said that this methyl group was in the axial position, what would the ethyl group be in? All right, so let's look here. Let's think back to our example here, right? We said it was this every other pattern, axial, equatorial, if they were all pointed in the same direction. So I'm 2 apart here, or 3 carbons apart here. So if they were both in the same direction, they would both be axial. But in this example here, this one's pointed down, or it's in the opposite direction, so this one would be in the equatorial position. And then if I did my flip, I would change my axial into equatorial and equatorial into axial. And which one of these is going to be more stable? The one on the left. All right, so we could have answered this question by drawing those chair conformations, but of course that would just take longer as a strategy. So I'm hoping like seeing this pattern makes it clear that you could answer this question without having to actually do the chair conformation. What's up?
Why is the one on the left more stable?
Oh, because the bigger group, this ethyl group is in the equatorial position, right? And it's all about making the larger the group, the more it's going to prefer that equatorial position. Cool. All right, so we'll kind of do the same thing next class as well. We'll take another sort of example of some biomolecules, talk a little bit about biochemistry, and use that to segue into some review from the first semester.